The term cybersecurity has been coined into a singular word, but it is very evidently made up of two separate terms. Cyber, which refers to everything that comes under the digital culture, and security, which is the art of protecting or hiding an entity. So when you put the two terms together, it basically means the protection of everything that is digital. Well, that in itself makes it a very vast topic, including domains like application security, information security, cloud security. But due to time constraints, I'm going to be discussing one of the most important domains in my opinion, and that is network security. So before we jump in, let me tell you guys that this whole video will be actually divided into two parts. So the first part will be discussing about the network. And when we are discussing about the network, we're going to go through a packet structure, how packets are transferred from one computer to another, network architectures including TCP/IP model and OSI based models, and all the type of addressing like multicast, broadcast, and unicast. And we'll also be going over protocols like address resolution protocols and how they can be hacked. In the security aspect, we're going to be discussing firewalls and the types of firewalls and the two different flavors of cryptography, namely symmetric key cryptography and public key cryptography. And in the end, we are also going to perform a very interesting demonstration as to how to perform a man-in-the-middle attack and what a man-in-the-middle attack can do to your system. Okay, so let's begin with our session today. Okay, so first we are going through the network part and I'm going to teach you all how a network actually works. Okay, so I think it's right to assume all of you watching this video have downloaded some sort of file in the past. Whether it be a movie, a TV show, some software, or music, you have downloaded something off the internet, but most of you don't really know how the whole process works. Now let me take a moment to explain the whole thing. So first of all, when you click that juicy download button, your whole file doesn't really get sent to you all at once. Rather, it is broken down into tiny units called packets, which are then transmitted over a network to your computer. Now, the way how atoms make enormous objects together, data packets come together to form one big file. They can be considered the atom of a network, and like an atom, a data packet too has a pretty complex structure which can be broken down into three significant parts, namely the packet header, which generally contains critical information about where the packet is coming from and where it is headed, the payload, which is basically the data contained by the packet, and the packet trailer, which is just data to signify the end of a packet. Now, out of the three, the packet header is the most important to understand when understanding the structure of a network, so let's have a deeper look at it. Okay, now what you see on your screen at this moment is an IPv4 packet header. A little bit on IPv4 before we continue is that IPv4 is the fourth version of the internet and it is also the most widely used digital communication protocol. There's also IPv6, but it hasn't really been implemented widely. And about IPv5, well, let's say it's what Microsoft did with Windows 9. It doesn't exist. Now, it's pretty evident from what we look at that the IP header indeed is a complex structure with numerous parts. The IPv4 packet header consists of 20 bytes of data. An option part also exists within the header that allows further optional bytes to be added. But this is not normally used, with the occasional exception of something called a router alert. Now let's take a moment to discuss all the header files briefly. So first of all, we have the version part. Now this is always set to 4 in the current IP version, and it shows the version of the protocol that we are following. Next is the header length or the IP header length, and it's a number of 32-bit words forming the header, which is usually 5. Next is the DCSP field, which is for differentiated service code point. It is a 6-bit field, sometimes set to 0, but can indicate a particular treatment, sometimes reflecting the quality of service, needs of an applicant to the network, and the DCSP informs a router how to queue packets while they are waiting to be forwarded. Next is the ECN field, which stands for Explicit Congestion Notification, and it tells us about the congestion in the network route. Next is this total length, which is the size of the datagram, and this is in bytes, and this is the combined length of the header and the data together. Next comes the identification field. Now, the identification field is a 16-bit number which, together with the source address, uniquely identifies a packet that is used during reassembly of a fragmented datagram. Next is the flags part. Now, there are a sequence of 3 flags. One of the 4 bits is unused and used to control whether the routers are allowed to fragment a packet and to indicate the parts of a packet to the receiver. Next is the fragmentation offset, and this is the byte count from the start of the original send packet sent by any router which performs IP router fragmentation. Next is time to live. Now, time to live is the number of hops or links which the packet may be routed over or decremented by most routers used to prevent accidental routing loops. It's a very important aspect of every packet. Next comes the protocol. Now, the protocol is a service access point or SAP, which indicates the type of transport packet being used and carried. For example, if it's 1, it's ICMP, if it's 2, it's IGMP, if it's 6, it's TCP, and if it's 17, it means it's following the UDP protocol. Next is the header checksum. Now, a once complement checksum is inserted by the sender and updated whenever the packet header is modified by a router, and it is used to detect processing errors introduced into the packet inside a router or bridge, where the packet is not protected by a link layer cyclic redundancy check. Now, packets with an invalid checksum are discarded by all nodes in an IP network. The checksum can be thought of something like a barcode. If the barcode gives you wrong information, you just discard that packet. Now, as you guys can see, the next field is the source IP address, and it is the IP address of the original sender of the packet. And next is the destination address, which is the destination field of the packet. And then we spoke about the options field. Now, it is not normally used, but when used, the IP header length will be greater than 5 32-bit words to indicate that the size of the option field has been included. Now, the Internet Protocol has been there for a long time, and there has been a couple of models that have really given the protocol a structure. The first model is called the OSI model, and the second TCP/IP. Now, both these protocols have a layered stack architecture, with each layer having very similar functionalities. First of all, let's have a look at the OSI model. Now, communications between machines is hard. Many details and considerations are important in order to relay some information from point A to point B, and therefore every system is left on its own and has a tendency to be very different. The OSI layer model was made as an effort to divide the process of communication into a number of steps, so every step could tackle some of the needed functions of the transmission separately. Now let me use a very strange analogy to explain all the functions of each of the layers in the OSI model. So suppose you want to send a number of objects, let's say a group of vases, to a friend of yours that lives on the other side of the world. He needs the said vases in order to put on some plants on a display. Now you and your friend represent layer 7, which is the application layer, which makes the final use of the sent object. Now you give this vase to another person. Let's call him a professional packer. He takes your vases, puts it in several boxes, fills them with wrapping in order to prevent it from breaking, and closes the boxes completely. This professional packer represents layer 6, which is the presentation layer. Now this professional packer takes all the boxes, gives them to the guy, an arranger. Now he doesn't know what is inside the boxes, but he knows they all go to the same friend of yours, so he labels them appropriately. So far, he represents layer 5, and that is the session layer. Now, the arranger takes all the boxes down to an office who handles clients in dozens of other buildings. They keep in touch with hundreds of other agencies at the same time. They do not actually send the boxes, but they track them and know when a box for an order is missing, and so. These guys are layer 4, which is also called the transport layer. Now, one of the guys from the office actually takes all your boxes along with many others to a post office. This post office is the third layer. Here, it is given an address, the one of your friends, and this is the layer 3 that is called the network layer. Now, one of the guys from the post office takes all the boxes to a dock, and the guys at the dock pull all the boxes into a container. They know very little about what the boxes contain or where their final destination is. They only care about which other dock is this container headed to. Now this dock is representing layer 2, which is the data link layer. And finally, we have the ship. It only knows where it is headed and takes the container with it. It handles the waves, the conditions of the sea, the weather, and all the other physical conditions that none of the other layers have to deal with. The ship is layer number 1, which is the physical layer. Now after all this, the ship gets to port, the containers are opened out here. Now boxes which are meant for this address stay on the dock, and the others are put into other containers and another ship and sent on its own way. Now all the staying boxes are sent to an associated post office, and layer 2 has done its job. Then the post office receives the boxes, maybe realizing some are missing. They call the sending post office to check what happened, and once they are sure all the boxes are there, they send it to the big office, and now layer 3 has done its job completely. Then the big office gets the boxes, checks they are all in the correct order and place, fill the relevant tracking data, and send them to your friend's arranger, and layer 4 has done its job completely. Then the arranger reads the label put by your arranger, and he makes sure everything is in order. He knows they are for your friend and calls the professional packer. Here, layer 5 has completed its job. Then the professional packer takes everything from the boxes, checks if everything is intact, and if everything is okay, he calls your friend, and layer 6 has done its job. And finally, your friends get the vases, happily unaware of everything that happened on every layer. He sets up the plants on display and is happily continuing with his day. Now, this is how the OSI layer model has actually differentiated all the different steps that you need for one packet to reach from one computer to another. I hope that analogy helped you all understand how a packet actually travels from one computer to another. Okay, so it's time now that we discuss the TCP/IP model. TCP/IP specifies how data is exchanged over the internet by providing end-to-end communication that identifies how it should be broken into packets, addressed, transmitted, routed, and received at the destination IP. Now, TCP/IP requires a little central management, and it is designed to make networks reliable with the ability to recover automatically from failure of any device on the network. The advantage of TCP is that it is non-proprietary, and as a result, it is not controlled by any single company. Therefore, the Internet Protocol suite can be modified very easily. It is compatible with all the operating systems, so it can communicate with any other system on the network. And the Internet Protocol suite is also compatible with all types of computer hardware and network types. Now, the TCP/IP functionality is divided into 4 layers, each of which includes a specific protocol. The application layer provides applications with standardized data exchange. Its protocols include Hypertext Transfer Protocol, which is HTTP, File Transfer Protocol, which is FTP, Post Office Management Protocol, which is POP3, Simple Mail Transfer Protocol, SMTP, and Simple Networking Management Protocol, which is SNMP. Next is the transport layer. The transport layer is responsible for maintaining end-to-end communication across the network. TCP handles communication between hosts and provides flow control, multiplexing, and reliability. The transport protocols include TCP and a user datagram protocol, which is sometimes used instead of TCP for special purposes. Next, we have the network layer. Now, the network layer, also called the internet layer, deals with packets and connects independent networks to transport the packets across network boundaries. The network layer protocols are the Internet Protocol, which is the IP protocol, and the Internet Control Message Protocol, which is also abbreviated as ICMP. Last but not the least, we have the physical layer. Now, the physical layer consists of protocols that operate only on a link. That is the network components that interconnects nodes or hosts in the network. The protocols in this layer include Ethernet for local area networks and Address Resolution Protocol. So now that we've discussed the models which describe the architecture, let's move on to the different ways packets can be addressed to other devices. Majorly, 3 main ways of addressing, namely unicast, broadcast,